Jai Hind everyone. Myself Dr. Vandana Sharma from Ajay Kumar Garg Engineering College, Ghaziabad. Today I'm going to discuss numerical problems which are related to superconductivity. So this particular topic that belongs to engineering physics, and code of this particular subject is BS 101 in first semester, and in second semester it is BS 201. So this particular topic that is superconductivity, that belongs to unit number 5 of engineering physics. So today I'm going to discuss numerical problems of this particular topic. But before going into those numerical problems, let's see that which parameters or what type of parameters we are going to discuss in today's lecture. So superconductivity that is actually depends upon various factors. There are certain metals, ceramics, alloys, which shows this phenomena of superconductivity at a very low temperature. And the temperature below which the material will show this superconducting behavior, that temperature is known as critical temperature. In addition to critical magnetic field, in addition to critical temperature, there is one more factor which decides the behavior of a superconductor, and that factor is known as critical magnetic field. So if you have a material which is having temperature T less than Tc, and if that material is having this potential that it can show superconductivity, then at this temperature, when T is less than Tc, that will be in superconducting state. But even at that temperature, when T is less than Tc, we can change the state of that superconductor from superconducting state to normal state. Means, just by applying an external magnetic field, we can change the state from superconducting state to normal state. So that factor, that minimum value of magnetic field, which is required to change the superconducting state, that is known as critical magnetic field. So the second deciding factor for superconductivity is our critical magnetic field. Now the third parameter which decides the superconducting behavior, that is critical current. And indirectly, this critical current is also associated with critical magnetic field. So basically, the numerical problems which today I am going to discuss, that is related to these three parameters. The first one, critical temperature. The second one, critical magnetic field. And the third one is critical current, which is indirectly associated with current density. So I'm going to discuss problems based upon these parameters. So let's have a quick recap about critical magnetic field. So as I have mentioned that a superconducting material that will show superconductivity only at a temperature when T is less than Tc. Means below critical temperature, material will be in superconducting state. So as you can see in this graph, along x-axis we have temperature, whereas along y-axis we have magnetic field. And this Tc is the critical or transition temperature below which the material is in superconducting state. And above this temperature, obviously material will be in normal conducting state. But between 0 and Tc, this particular behavior, this superconducting state, that can be destroyed, and we can regain the normal conducting state just by applying an external magnetic field. So that minimum amount of magnetic field which is required to destroy the superconducting behavior, that at a temperature T less than Tc, that minimum amount of magnetic field is actually known as critical magnetic field of that temperature. I hope this particular point is clear. For example, suppose you have mercury for which critical temperature is 4.2 Kelvin. So below 4.2 Kelvin, obviously mercury will be in superconducting state. Now below this 4.2 Kelvin, I am taking a temperature 3 Kelvin. So at 3 Kelvin, this particular magnetic field, that is the minimum amount which is required to change the state of mercury from superconducting state to normal state. So critical magnetic field is actually the minimum magnetic field required to change the state of material from superconducting state to normal state. This critical magnetic field is having significance, or it is having meaning, or it will play its role only between 0 and Tc. Above Tc, obviously material will be in normal conducting state. So this particular factor is totally insignificant. So between 0 and Tc, you have different values of critical magnetic field for a certain superconducting material. For example, you can see here at 0 Kelvin, the amount of magnetic field, the amount of critical magnetic field which you require to change the state of material, that is maximum between 0 and Tc. And at critical temperature, you do not require any magnetic field to change the state of material. And in between 0 and Tc, at any temperature T, which is less than Tc, this critical field is given by this particular expression, where HCT is known as critical magnetic field at temperature T, where T is less than Tc. Hc naught, this Hc naught, that represents the critical magnetic field at 0 Kelvin. And as I mentioned that at 0 Kelvin, we require maximum critical field for any material. So this Hc naught, that represents the critical magnetic field at 0 Kelvin into 1 minus T square upon Tc square, where this T is the temperature at which we are defining this critical magnetic field, and this Tc, that is the critical temperature, or you can say transition temperature, below which the material will move from normal conducting state to superconducting state. So that is a transition or critical temperature. So this is a formula. Now, using this particular expression, using this mathematical expression, which actually the outcome of this particular graph, we are going to solve different numerical problems. So let's see how to approach those problems related to critical magnetic field and critical temperature. So here we have this particular problem number 1. In this problem, there is a superconducting material, and that material is actually lead. Its critical temperature is given. It is 7.26 Kelvin. So 7.26 Kelvin is the transition temperature. The initial field at 0 Kelvin is 64 into 10 raised to power 3 ampere per meter. Means the critical magnetic field at 0 Kelvin is defined. It is 64 into 10 raised to power 3 ampere per meter. Calculate the critical field at 5 Kelvin. So I hope the question is clear. You have a superconducting material, and that superconducting material is lead. Along this direction, we have temperature. Along this direction, we have critical magnetic field. This critical temperature is 7.26 Kelvin. Now, below 7.26 Kelvin, we have this temperature, which is 5 Kelvin. And according to the question, the critical field at 0 Kelvin is also given. This is 0 Kelvin. So, at 0 Kelvin, the critical field, which is the minimum amount of magnetic field required to destroy the superconducting state, that is 64 into 10 raised to power 3 ampere per meter. So now we have to find this critical field at temperature 5 Kelvin. So we have to find the critical field at 5 Kelvin. So we know what is the expression for critical field in terms of temperature. So this is a formula. Critical field at temperature T is equal to Hc naught into 1 minus T square upon Tc square. So first, try to identify what is given in the question. So write all the terms which are given in the question. So in this question, critical field at 0 Kelvin is given, as well as critical temperature is also defined. And it is also given that we have to find the critical field at 5 Kelvin. So what we have to do, we have to substitute all these values in this particular equation. Like this is equation number 1. So you have to substitute these values here. In place of Hc naught, we will substitute 64 into 10 raised to power 3 into 1 minus T. T is replaced by 5 Kelvin and Tc is 7.26 Kelvin. So just substitute these values. So when you will substitute, then Hc at 5 Kelvin is, this is Hc naught, 64 into 10 raised to power 3, and it is in ampere per meter. 1 minus T is 5 and Tc is 7.26. So we have to simplify this particular term, and after the simplification, the value of this particular parameter, that is 0.5257. So you have to multiply that 1 minus T square upon Tc square with Hc naught. This is your Hc naught. So when you will multiply this, you will get the critical field which is required to destroy the superconducting behavior at 5 Kelvin. So this is the minimum amount of magnetic field which is required to change the state of material from superconducting state to normal state at 5 Kelvin. Now, there is one point which you need to observe here carefully, that the critical field at 0 Kelvin is having maximum value. So it is 64 into 10 raised to power 3 ampere per meter. As the temperature will increase, as you can see from this graph, with the increase in temperature, that critical magnetic field will decrease. So obviously, at 5 Kelvin, that critical magnetic field will have a lesser value than Hc naught. So that value is 33.64 into 10 raised to power 3 ampere per meter. So this is the method to find the critical field at any given temperature, which is less than the critical temperature of the given superconducting material. So let's take another problem. So this is our second problem. As you can see here in this problem, the critical field for lead is 1.2 into 10 raised to power 5 ampere per meter. And this particular critical magnetic field is at 8 Kelvin. So this value is given at 8 Kelvin. And the critical magnetic field is 2.4 into 10 raised to power 5 ampere per meter at 0 Kelvin. So this Hc naught is at 0 Kelvin is Hc naught is 2.4 into 10 raised to power 5 ampere per meter. Now we have to find the critical temperature. So now the question is that if you have critical magnetic field at 0 Kelvin and if you have critical magnetic field at some other temperature, then how to find the critical temperature? So again, you are going to use the same same mathematical expression which we have already discussed, that Hc T is equal to Hc naught into 1 minus T square upon Tc square. Now first identify that what is given in this question. So in this question, again along y-axis we have magnetic field and along x-axis we have temperature. So in this case, the critical magnetic field at 0 Kelvin is given, and this particular value is 2.4 into 10 raised to power 5 ampere per meter. In addition to that, the critical field at 2 Kelvin is also given. So, at 8 Kelvin is also given. So this is 8 Kelvin. So at 8 Kelvin, this is 1.2 into 10 raised to power 5 ampere per meter. So these are the two critical magnetic fields, and we have to find this critical temperature. So in order to find that critical temperature, first just identify what is given in the question. So as we have already discussed here, all the given terms are mentioned over here. Critical magnetic field at 8 Kelvin, at 0 Kelvin, and the temperature which is in between 0 and Tc, that is 8 Kelvin here. So we will simplify this particular mathematical expression for the required parameter. So basically the parameter which is required in this numerical problem is critical temperature. So first we will try to simplify this mathematical expression for Tc. So from here you can see 1 minus T square upon Tc square is Hct upon Hc naught. Further, if you will simplify this, then T square upon Tc square is 1 minus Hct upon Hc naught. Now this Hct is basically Hc8 and Hc naught is this particular value. So first simplify it for Tc. So if you will simplify it for Tc, then this Tc will be equal to T upon under root 1 minus Hct upon Hc naught. So basically this T is your 8 Kelvin upon under root 1 minus Hct, which is Hc8 actually, which is 1.2 into 10 raised to power 5 ampere per meter. Hc naught is 2.4 into 10 raised to power 5 ampere per meter. So if you will see these two terms, then it is only 1 by 2. So 1 minus half, that will be 1 by root 2. So it will be 8 root 2 Kelvin. So after simplifying, after substituting the value of that root 2, this critical temperature that is equal to 11.31 Kelvin. So this is the way, this is the method through which you can find the critical temperature if you have critical magnetic field at if the critical magnetic field at two different temperatures are given. So following this particular method, you can find the critical temperature of any superconducting material. So this is our problem number 2. Now let's take another problem. In this problem, a superconducting material has a critical temperature of 3.7 Kelvin. Right? So first term which is given over here, that is its critical temperature, which is 3.7 Kelvin. In zero magnetic field and critical magnetic field of 0.02 Tesla at 0 Kelvin, means its critical magnetic field at 0 Kelvin is also mentioned, and it is 0.02 Tesla. Now the question is, we have to find the critical field at 3 Kelvin. So again, you have same graph. Along this direction we have magnetic field, along this direction we have temperature. So in this particular question, this critical temperature is defined. It is 3.7 Kelvin. In addition to that, at 0 Kelvin, this critical magnetic field is also defined, and it is 0.02 Tesla. Right? So what we have to do, below this Tc, a temperature 3 Kelvin is given, and at that temperature of 3 Kelvin, we have to find that what is the minimum amount of magnetic field which is required to destroy this superconducting behavior. So we have to find this Hc at 3 Kelvin. So this is our question. So again, we are going to adopt the same method. First, identify what is given in the question and mention all these terms. So Hc naught is given, critical temperature is also given, and the temperature at which you have to find the critical magnetic field, that is also mentioned. So what you have to do, simply you have to substitute the values here. So Hc at 3 Kelvin, that will be Hc naught, which is 0.02 Tesla actually, into 1 minus T. T is 3 Kelvin and Tc is 3.7. So just substitute these values and simplify this particular term, and then get the value of 1 minus T square upon Tc square, which comes out to be 0.3439. So just multiply this particular term with 0.02 Tesla. If you will multiply it, then you will get the critical magnetic field at 3 Kelvin, which is 0.0068 Tesla. And obviously, you know the critical magnetic field at 0 Kelvin, that will be maximum for a particular material. So 0.02 Tesla, that is the maximum amount of magnetic field which is required to destroy the superconducting behavior, and that will be at 0 Kelvin. And if you will increase the temperature, obviously the critical magnetic field, its value will decrease with the increase in temperature, because between 0 and Tc, the superconducting behavior, that is sum total of that temperature and critical magnetic field. So if the contribution of temperature will increase, then obviously the contribution of critical magnetic field will decrease. So you can see here the critical magnetic field at 3 Kelvin is having a smaller value than the critical field at 0 Kelvin. So the result is 0.0068 Tesla. So these were some problems based upon critical magnetic field, that how to find the critical magnetic field at any temperature T, which is less than Tc, as well as how to find the critical temperature of a certain material if you have critical field at two different temperatures. Now the next term or next parameter whose numerical we are going to solve, that parameter is critical current. So basically, as we have seen here, that below critical temperature, when the superconducting material, that is in superconducting state, we have seen that the superconducting behavior that can be destroyed just by applying an external magnetic field. So if you will apply an external magnetic field, then at a particular value of magnetic field, the material will move from superconducting state to normal state. So now it is not necessary that by using a source of magnetic field, you have to apply the magnetic field and change the state of material. You can do one thing. You have a superconductor, and a superconductor itself means zero resistivity, means easily you can flow current through that superconducting material. So if you will pass current through a superconducting material, then obviously around the superconducting material, there will be magnetic field. So if the current which is passing through the superconducting material at a temperature T, which is less than Tc, is giving you a magnetic field which is equal to the critical magnetic field of that temperature, then that particular current is known as critical current. I hope you are getting this point. I am repeating it again. At temperature T, which is less than Tc, if you will pass current through a superconducting material, that current will give you a magnetic field. And if that current can produce a magnetic field equal to the critical magnetic field of that temperature, then superconductivity will be destroyed and you will regain the normal conducting state. So that minimum amount of current which is required to change the state of material from superconducting state to normal state at a temperature T less than Tc, that current is known as critical current, right? So we can easily correlate this critical current with critical magnetic field just by applying Ampere's law. You all know that according to Ampere's law, the closed line integral of magnetic field is equal to mu naught times the current enclosed. If you will use this particular expression, then you can write the relationship between this magnetic field and current. So H is equal to I upon 2 pi r. So if I'm saying the current which is flowing through the superconductor that can produce a magnetic field equal to critical magnetic field of that temperature, then the current which is passing through the superconducting wire, that is known as critical current. So if H is Hc, then I will be Ic. So the formula for critical current is Ic equals to 2 pi r Hc. So this is the relationship between critical current and critical magnetic field. If this is a formula for critical current, you can easily define critical current density. You all know that critical current density, current density is actually the ratio of current and area. So this Ic, when we are talking about critical current density, then it will be critical current upon area. So this will be Ic upon IR square. So now we will see that how to find this critical current and critical density, critical current density. So we have this particular problem. Find a critical current which can pass through a long thin superconducting wire of aluminium of diameter 2 millimeter. So the first parameter which is given, that is diameter of this particular superconducting wire, and that is 2 millimeter. So if D is 2 millimeter, then obviously radius is 1 millimeter. The critical magnetic field for aluminium is 7.9 into 10 raised to power 3 ampere per meter. So critical magnetic field is also given. So we have to find the critical current as well as critical current density. So let's see how to simplify, how to solve this particular problem. So Ic, the critical current, as you know from our previous discussion, that Ic will be 2 pi r Hc. Since the critical magnetic field is given over here and radius of that superconducting thin wire is also given, so you can easily find this Ic. So first identify what are the parameters given here. So Hc is given, this is the value of Hc. R is 1 millimeter, and since this magnetic field is an ampere per meter, we have to convert all the parameters in same unit. So R, that is in meter, as 0.001 meter. So Ic, obviously, according to the formula, it will be 2 pi r. This is the value of r, and this is value of Hc. Just simplify it, you will get the critical current for this superconducting wire. And when you will simplify, this critical current for the superconducting thin wire is 49.61 ampere. So if this is a value of critical current, then easily you can find critical current density, which will be equal to critical current upon area. So that will be Ic upon IR square. Just substitute these values. So Jc is Ic upon A. Ic from this equation, it is 49.16. Area, that is pi r square. So R, that is given over here. So if you will simplify it, you will get the critical current density for this superconducting wire. So this is the method through which you can find the critical current which is required to destroy the superconducting behavior of a superconducting wire, as well as you can find the critical current density for a superconductor. Okay. Let's take another problem, and in this particular problem, the critical fields for lead are 1.2 into 10 raised to power 5 ampere per meter, and 3.6 into 10 raised to power 5 ampere per meter. And these critical magnetic field, actually these fields are defined at two different temperatures. The first field, this is at 12 Kelvin, and the second field, this particular field, this is at another temperature, which is actually 10 Kelvin. We have to find the critical temperature or transition temperature, as well as the critical magnetic field at 0 Kelvin and critical magnetic field at 3.2 Kelvin. So we have to find three different parameters in this question. The first one, we have to identify its transition temperature by using these two relationships or these two informations. That is one at critical field at 12 Kelvin, and the other information is that we have critical field at 10 Kelvin. Then we have to find the maximum amount of critical magnetic field, which is at 0 Kelvin, as well as critical magnetic field at 3.2 Kelvin. So first, let's try to find out that what is its transition temperature. For this, we have this formula, HCT is equal to HC naught 1 minus T square upon Tc square. So in case number 1, we are taking this temperature as 12 Kelvin. So when we will take this temperature as 12 Kelvin, at 12 Kelvin, it is given that this HC12 is 1.2 into 10 raised to power 5 ampere per meter, as well as critical field at 10 Kelvin is also given. So we have to use these two relationship or these two informations. HC12, according to this formula, it will be HC naught into 1 minus, just substitute T as 12 Kelvin, 12 square upon Tc square. And for the second case, we are taking temperature as 10 Kelvin. So HC10, it will be HC naught into 1 minus 10 square upon Tc square. So now we have this information. We have HC12 as well as HC10. So we have to simplify these two equations. Let this is equation number 1 and this one is equation number 2. So if you will divide equation number 2 by 1, you will get HC10 upon HC12. So these two factors will get cancelled. And if you will simplify this will be Tc square minus 144 divided by Tc square. And in denominator, second factor, that will be equal to Tc square minus 100 divided by Tc square. So when you will divide equation number 2 by 1, you will get HC10 upon HC12 as Tc square minus 100 divided by Tc square minus 144. And you have this HC10 as this one and HC12 as 1.2 into 10 raised to power 5. So these two factors will give you only 3 value. So you have Tc square minus 100 divided by Tc square minus 144 as 3. Just simplify this. So when you will simplify, you will get 3 Tc square minus 432, that is equal to Tc square minus 100. Just simplify it for Tc. When you will simplify, then this Tc square will be 166. So after taking under root, you are getting the critical temperature of this particular material, and that critical temperature is 12.88 Kelvin. So it means if the critical field at two different temperatures are given, then you can easily, by adopting this method, you can find the critical temperature of that superconducting material. So this critical temperature is 12.88 Kelvin. Now the next thing is we have to find the critical field at 0 Kelvin. So you can take the expression of critical field at 12 Kelvin or 10 Kelvin. Either by using HC12 or HC naught, you can get the required expression for HC naught. So HC12 is equal to HC naught into 1 minus this 12 square upon Tc square. So as we already know from our calculation that Tc is 12.88. So after simplifying, you are getting this HC12 is HC naught into 0.132. So what you have to do now, you have to substitute the value of HC12 here. So after substituting its value, you are getting the critical field at 0 Kelvin, that comes out to be 9.1 into 10 raised to power 5 ampere per meter. So this is a way to find the critical field at 0 Kelvin. Now the last part of this question is that we have to find the critical field at 3.2 Kelvin. So you know the formula that HC 3.2 is equal to HC naught 1 minus 3.2 square upon 12.88 square. So if you will simplify it, you will get the value of critical magnetic field at 3.2 Kelvin. Right. So this is a way to find these three different parameters here. Now another question. Find the temperature at which the critical magnetic field becomes half of its value at 0 Kelvin. So you have to find that temperature at which the critical magnetic field is half of its value at 0 Kelvin. So this is given in the question. If the critical temperature of superconductor when no magnetic field present is Tc. So the critical temperature is given as Tc here. So we have to find, so this is very easy. What you have to do, you have to use this particular relationship. HCT is equal to HC naught 1 minus T square upon Tc square. So what you have to do now, you have to substitute this HCT as HC naught upon 2. So when you will substitute this as HC naught upon 2, it will be HC naught into 1 minus T square upon Tc square. So this HC naught that will get cancelled and you will get your T square upon Tc square as 1 by 2. So our aim is to find the temperature at which the critical magnetic field is half of its maximum value. So this will be Tc upon under root 2. So this is the way to find the temperature at which the critical magnetic field is half of the maximum critical magnetic field, which is at HC naught. So if this critical temperature is given in the question, for example, the critical temperature is 8 Kelvin. So if it is 8 Kelvin, then obviously you will get the value of T as 8 Kelvin upon under root 2. So this is a way to find this critical temperature. Right. So these are the reference books which you can adopt for this topic of superconductivity. So basically what we have discussed about the three parameters: critical temperature, critical magnetic field, and critical current. For critical temperature is that transition temperature below which the material is in perfect superconducting state, and above that temperature material is in normal conducting state. So critical temperature is the transition temperature at which you are getting the transition from one state to another. And superconductors, they will show this behavior only below critical temperature. But below critical temperature, by applying an external magnetic field, you can change the state of material from superconducting to normal state. So that you have seen that critical magnetic field is actually a function of temperature, and it is having different values at different temperatures. In the last third parameter, you have seen that it is not necessary to apply the magnetic field through any external agency or external source. What you can do, you can pass current to the superconductor, and if that current can produce a magnetic field equal to critical magnetic field, then that current is your critical current. So we have seen in this particular lecture that how to find that critical magnetic field, critical current density, and critical temperature. So that's all for today. Thank you very much.